Okay, so now we're going to go over and show how the Bernoulli equation and conservation of mass can be coupled together and sort of gang up to solve problems. And I'm going to do that by way of example. And what that example is we're going to consider flow through a reducer here. So we have a sort of nozzle, it's sometimes called a reducer, where you're going to take a section of pipe of one diameter and decrease the diameter of pipe to a smaller diameter. And so we'll call this station 1 in the big area, and the flow is moving from the big area to the small area. Okay? And we know the velocity 1, and we know the two areas, and we know that these 2 points are at the same elevation. Okay, and what we're asked to find is what is the pressure difference between this point and this point if this velocity and these two areas are known. So, as always, we write our assumptions. And the assumptions are, 1, we'll assume steady flow, we'll assume inviscid flow, and we'll assume constant density. And then with those assumptions, and we can easily consider a streamline between point 1 and point 2. This means these three with this streamline means that we can use Bernoulli. And also we will assume that the flow is uniform on these two areas, and we'll assume that the walls are impermeable. Okay, so now we can really start with the solution then. And so we're looking for a pressure difference, and we meet the criterion for the 4 criteria for Bernoulli. So we can apply Bernoulli. And so let's apply Bernoulli. So we know that Bernoulli states that P1 plus 1/2 rho, it's a really bad rho, that basically 1/2 rho of V1 squared plus rho GZ1 is equal to P2 plus 1/2 rho V2 squared plus GZ2. And these two are at the same elevation, so we can cross them out. So we don't need to do anything with that. And so we basically have our P1 and P2 here, and we just solve for the pressure difference. And in doing that, we find that the pressure difference is just 1/2 rho. Again, it's constant rho, so it's the same here as it is over here, is just equal to the differences between the velocities squared. Okay, unfortunately, we don't know V2. And to find V2, we need to apply a conservation of mass. Okay, and to apply conservation of mass, of course, we need a control volume. And again, in your homework, show the control volumes at all times. Okay, and so we have our reducer here. This here is the exit of it. And again, we walk around this counterclockwise. And n hat on the right will point to the right. And so n hat at station 2 will be I hat. And the velocity will be the velocity at station 2. And again, the flow is going from left to right. So it is going in the I hat or x direction. Okay, and we got the sides. Those are impermeable, so they're not going to contribute. But then we go down, and now we're at station 1. Well, again, n hat 1 will point to the left. Again, it points to the outside of the control volume. So that is minus I hat. And we have some V1 I hat coming in. Okay. So now we have our control volume drawn. We have the velocities and everything drawn on that. So now let's apply conservation of mass. And again, even though this is a stationary control volume, which I'm defining it to be stationary, I'm starting with this generic form. Just because, and I'll show you how easily you can reduce this to the stationary form. So always in your homework, start from this generic form after we've gone over it. Okay, well, the flow's steady. So we can cross out that term. And then we're assuming constant rho, so we can pull that out of the surface integral. And this is a stationary control volume, which implies that the relative velocity is just equal to the fluid velocity. Like that. Okay, and so what we wind up with is that conservation of mass reduces to the surface integral of the fluid velocity dotted with n hat dA. And so you can see that this, that basically starting here and just putting an extra little half step, arguing that the control volume is stationary, reduces it to the normal, reduces the more general form to the stationary form in one nice step. Okay, so now we need to form the surface integral here. So we then walk around the control volume surface, or the control surface, and we just keep tabs on all the pieces and break the integral into the three pieces, as always. So we have the integral over the inlet, plus the integral over the outlet, plus the integral over the walls. Well, we're assuming the walls are impermeable, so no mass is crossing through them. Which means that v dot n hat is equal to 0, or v xyz dot n hat is equal to 0. Okay, so now we need to work with these integrals here. And since this case is quite simple, I'm not going to do the normal bookkeeping way that I do it. Instead, I'm just going to do them right underneath the integrals here. So we can now work with this. We have all the I hats drawn. We know in this diagram here that n hat 1 is equal to minus I hat, and v1 is equal to the velocity magnitude at station 1 times I hat. And so we take these and then dot them together, and we get minus v1. Okay, then this equals, we then take this, stuff it into here, and we get this integral here. Well, this is uniform, so then we can basically pull that out, because that means that basically v1 at the top of the surface is equal to v1 at the bottom of the surface. So it's spatially uniform over the area, so we can just yank that out. And then this is what the integral turns into. And then we can basically do the same thing for the second area. I'm not going to go through that in detail. Okay. And we wind up with that, basically this integral here of basically minus v1 dA1 plus the integral of v2 dA2 is equal to 0. Again, these are both uniform. We can pull them out of the integral. And in doing that, what you wind up with is that minus v1 a1 plus v2 a2 is equal to 0. And we know v1, we know a1, we know a2. We can now solve for v2. And this implies that v2 is nothing more than v1 times the ratio of the two areas, which makes complete sense. Okay. Then, so now we know v2, we can then go back to our original problem where we wanted to find the pressure difference. Recall that the pressure difference was just given by P2 minus P1 is equal to 1/2 rho times V1 squared minus V2 squared. And that equals 1/2 rho times V1 squared. And I'm going to take this result for V2 and substitute it into here. And I get this expression here. And then I go through and simplify. And I wind up with this expression here. And notice that if A1 is larger than A2, this term here, meaning that the inlet is larger than the outlet, this term here is greater than 1, which means that the pressure in the small area of our reducer is less than the pressure in the larger area of the reducer. And that's just a consequence of the flow needing to accelerate as it goes through a progressively smaller area until it reaches the exit. And so as the flow accelerates, you could argue that the kinetic energy that the dynamic pressure, or that the static pressure is being converted to dynamic pressure, and that the static pressure is basically necessarily being reduced as we accelerate the fluid. Okay, so in other words, the static pressure decreases as we accelerate the flow through a nozzle or an expander or something like that. Okay, and so this sort of shows an example of how we can couple Bernoulli with conservation of mass. Now I'll do a more complicated example where we need to string together Bernoulli, manometers, and conservation of mass. And so here we have water flowing in an inclined reducer. We have actually gravity acting straight down, which I should draw. Okay, so we have water flowing up through this reducer here. That's at some angle theta. And this reducer has a manometer stuck to the side, and the manometer fluid is oil, and the specific gravity of oil is less than 1. And all we know is that we have some volumetric flow rate V dot flowing through this pipe. And what we want to find is that for a given V dot, what is the height what is the height h of this manometer? Okay, and so that's essentially what we want to find. And so we need to make a whole litany of assumptions here. So for the assumptions, we again assume steady flow. We're going to assume that viscous effects are negligible, and we're going to assume uniform flow. Okay, and with these, and we could easily consider a streamline between this point and this point here. So this streamline, in conjunction with these three assumptions here, means that Bernoulli is applicable between these points. Okay, and we're going to assume incompressible flow, uniform flow. And that means constant. Excuse me. Not these three assumptions here. These two assumptions plus this one assumption here means that we can use Bernoulli. Excuse me on that. Okay, and we will assume static fluid in the manometer, which means that we can use our results for fluid statics inside of the manometer. And we will assume that the diameter of the tube is much smaller than this height h. Okay, and that assumption will come in useful later on. Okay, so the solution, as you can see, this is a pretty complex little system, and to solve it, we need to string together manometers, Bernoulli, and conservation of mass. Okay. So I guess solving a problem like this is a bit like eating an elephant, and you just do it by one piece at a time. And so the problem is asking for what this h is. So first, let's just start with the piece of a solution that where we can find h, or that involves that height h, and that height h is involved with the manometer. So why don't we first start with the manometer find a relationship for H, and then see what we need to find that relationship. Okay. Okay. So what we'll do now is I redrew it. I have G going down, and I added some links here. So point 1, I'm going to call that at the center of the channel here, and point 2 is at the center of the channel here. And then there's a point 1 prime, which is basically just underneath which is just at the pressure tap right here. And there's a point 2 prime right here, which is also just barely underneath the manometer tap on the right side. Okay, now we are looking for this height H here. Now, when we go through the manometer loop between point 2 prime and 1 prime, we'll have this height L here. We don't know what that is. Spoiler alert, you will find out that those do cancel out, and you don't need to know what that is. Then we got the distance between here and here. And this distance here will be this distance here will be Z2 prime minus Z1 prime. Okay, and so I just had to draw some extra distances on this manometer just so that we can completely enclose the loop between 2 prime and 1 prime. And so I'm going to start with this loop here, and then we're going to use this assumption here to basically argue that the pressure difference between these 2 points here is the same as the pressure difference between these 2 points here that we actually want. Okay? And so we'll start and we'll apply the manometer relations to find the pressure difference between point 2 prime and 1 prime, like I said before. And the manometer relation state that P end minus P start is equal to the sum of the rho G delta H's. And now remember that delta H for a manometer is negative if you're going against gravity in a portion of the loop, and it's positive if you are going in the direction of gravity for another portion of the loop. And our loop will start at point 1 prime and it will end at point 2 prime. Okay. Okay, and so we just apply the manometer relationship. So P2 minus P1 prime. Well, first we start in the water. So that's rho H2O is rho G, and we go up from point 1 prime here to the elevation of point 2 prime. So that's so that height is Z2 minus Z1 prime. Then we go up another L. Then we go up our height H. Okay, and so we have started here. Now we are here in the loop. Okay, so we are in the water. And again, we are going against gravity, so there's a negative sign right there. Now we go up some distance, over and down. Well, here along this line here, we did not cross into a different fluid. So the pressure here is the same as the pressure here. So when we go through the loop, we can then restart over here. And now we are in the oil, and we're going to go down a distance H. So we add a rho oil times gravity times H down. Now we are here. Now we got this last little piece here, and we are in the water again. And we're going down a vertical distance L. So we add a rho H2O times G times L. And I mentioned this before, but manometers are those things that we will be using all the way through the end of the class. And for the density of the oil, we can just use the specific gravity times the density of water. Okay, so essentially here, what we find is that this L here and that L there, those cancel out. We don't need to know what they are. And so, which is super nice. Okay, and so now this implies, we can simplify this a bit. This implies that P2 prime, which is right here, minus P1 prime, which is right there, is equal to minus this piece here, missing H, and just this piece here. Those are the only two that survive. And of course, I'm replacing rho oil with rho H2O times the specific gravity. Okay. Now we are assuming uniform flow, and which basically means that the velocity is the same here as it is here, and that also means that the pressure is the same here as it is over here, where the fluid is moving. Or you could also argue that based on that this distance here is small compared to the distance in the manometer, we can then argue that P1, which is what we want, and P1 prime are essentially the same. And we can argue also that P2 prime, that P2 prime and P2 are essentially the same. And if this change of height is small, then also we can argue that Z2 prime minus Z1 prime is essentially the same as Z2 minus Z1. Okay? And that is usually the case. And again, you could also basically just make, you could also base this off of the uniform flow argument too. So there are multiple ways of doing this, is that essentially when you're doing problems like this, you don't need to worry about this small distance between the center line of the tube and the entrance to the manometer, unless the instructions for the problem explicitly state that you should do that. Or there's something egregious like the diameter of this tube is, I don't know, like 10 meters, and the height of the manometer is like half an inch. Okay, there you need to consider that. Okay, so we make that assumption and we substitute that in. Then we know then that P2 minus P1 is equal to rho H2O times H times G times SG minus 1 times our change in the elevation. Okay, so all I did was I just basically factored H and substituted in our simplifications for Z2 minus Z1 and P2 prime and P1 prime. Okay, so we then have this expression based on the manometer relationships, and we just solve for H. And we find that H, which is the final expression that we want, is equal to the pressure difference plus rho g times the change of the elevation between station 2 and station 1, divided by rho H2O times g times the specific gravity of the oil minus 1. But unfortunately, we do not know P2 minus P1. So we need to do something with this term here, because I never gave you P2 and P1. Okay? So now what? Well, so we need to think of a relationship that we know that satisfies our assumptions, where we can find a pressure difference. And essentially, this portion here is exactly the same, with the exception of the change of the elevation, as the flow through the reducer that I just showed you. And so we are assuming a steady inviscid flow with constant density, and you can easily consider a streamline between these 2 points. And so that means we meet the 4 criterion to apply Bernoulli. And then with Bernoulli, we can find that with Bernoulli, we can find that pressure difference. Okay, so we have all 4 conditions required for Bernoulli. And so we just apply Bernoulli, that P1 plus 1/2 rho V1 squared plus rho G Z1 is equal to P2 plus 1/2 rho V2 squared plus rho G Z2. And we can solve for the pressure difference, which is right here. Okay. Then P2 minus P1 is equal to this expression here. And I'm just substituting in H2O because it is H2O flowing through that reducer. And so now I'm going to take this long expression here and substitute it into our expression for H. And it looks like it looks like we're going to get a gigantic mess, but please bear with me on this. You'll be pleased about the result after it's done. So now we take this expression and we're going to sub it into our relationship for H that we found. And so I do that, we get this big long nasty thing here. But notice that these two terms here are equal and opposite. We have rho H2O times G multiplying both. In here we have Z1 minus Z2, and here we have Z2 minus Z1. So those are equal and opposite, so we can and so we can cancel those out. And then also we have rho H2O basically multiplying everything. So that also drops out. And so this big long nasty formula reduces to this nice tight compact formula here. Okay? And notice that it does not depend on the material, it does not depend on the elevation difference. That basically dropped out. The effect on the manometer and the Bernoulli equation basically canceled each other out, and that change of height does not matter, or the change of the elevation does not matter to the manometer, which to me is kind of a nice result. So now we don't know V1 and V2. We just know the volumetric flow rate through the channel, and so now we need to relate V1 and V2 to the volumetric flow rate, and we'll use conservation of mass to do that. Okay, and so as always, we draw a control volume here. So we have our reducer here. I'll call the exit plane again station 2. The diameter here is D, cap D, and the diameter at the exit is small d. And I have n hat 1 pointing down and to the right. Again, we are going around counterclockwise. So as we go around on station 2, n hat 2 points up and to the left, or points up and to the right. And we go around, and n hat 1 points down and to the left, and V1 goes in, and we have the impermeable walls. Okay, so again, the control volume looks the same, essentially the same as it did before, only it's basically rotated up by some angle theta. Okay, so now we will apply conservation of mass. Again, I start with the generic form, and then I like to cross out terms. And in your homework, I expect you to start from the generic form for a deforming control volume. So this is steady, so that term crosses out. Okay, and for this relative velocity here between the fluid velocity and the control surface, well, we're assuming a stationary control volume. So this relative velocity is just the velocity of the fluid. And we are assuming that density is constant. So we can also pull out this density outside of this integral. Okay, and so, and then again, we would have a density we would have basically a density times something is equal to 0, which means that that density does not matter. And just like we did before, what we wind up with is that the surface integral of v dot n hat dA is equal to 0. Okay, and so now, again, this circle here in the area integral over the control surface means that we need to walk around the entire surface and completely enclose the surface, our area integral. And so we're going to do that as we did before, and we break it into the 3 pieces. We have the portion at the inlet, which is right here, plus the portion at the outlet, plus the so-called sides or the walls. And we can cross these out over here, and we can cross them out for two reasons. One, we're assuming impermeable walls, but you could argue, wait a minute, but couldn't there potentially be flow turning into the manometer and causing some sort of flow going around? But we assume that the flow is static, in the manometer, and as far as the fluid is concerned, it is then not allowed to go into the manometer. So that's the same as an impermeable wall. Okay, so we don't need to worry about mass basically turning and going up into the manometer. If you choose this height here of the manometer improperly, you can get flows like that. But you just need to choose your manometer lengths here and the manometer fluid here appropriately, so that you do have static flow, so that you have a static fluid in the manometer. That is up to you as a designer designing it. Okay, so now, as before, we just basically work through these different areas here in a methodical fashion. And now for area 1, I'm just going to call this n hat 1. We don't really know theta, and I'm not going to do all the cosine stuff. I'm just going to call this some n hat 1. Okay, and I'm going to then assume, because we know that fluid is going in and n hat is pointing out, we know that they are in opposite directions. And so we're going to define to be that the velocity vector at 1 is just basically the velocity magnitude at 1 times negative I hat, because again, they are in opposite directions. Then that implies that v1 dot n hat 1 is negative v1 n hat 1 dot n hat 1. Well, n hat dot n hat, that's a unit vector, is just 1, and so we just wind up with minus v1. Okay, so then we can take this result and stuff it into the area integral as we did before. Okay, and so we take this result here and substitute it into here. And again, we're assuming uniform flow, which basically means that we can basically take this and yank it outside. And we get, this is equal to minus v1 times the integral over the area of dA. And this here is nothing more than the area. And this equals to minus v1 times a. And this here is just equal to negative v dot, because again, this is the definition of a volumetric flow rate. And this here is just the volumetric flow rate at station 1. And in reality, you normally don't have to go through all this extra stuff here. You could argue that this here is by definition just the volumetric flow rate, because that's directly what we are given. You just need to make sure and basically argue that there's a negative sign by this volumetric flow rate, because n hat and the velocity vector are pointing in opposite directions, which means that flow is going inside of the control volume through that portion of the control surface. Okay, and now we go through and repeat the same thing for area 2. I'm going to now, for area 2, v2 and n hat 2 are pointing in the same direction. So basically v2 is just the velocity magnitude at station 2 times n hat 2, which we don't know, but we don't have to know what it is. The same thing is going to happen for area 2 as it did for area 1. Then we take their dot product and we just wind up with v2. We again shove it into the integral, assume uniform flow, and then we wind up with this, and we wind up with that v2 a2 is equal to the volumetric flow rate leaving the control volume through station 2. So now we have that this nasty integral here just turns into the volumetric flow rate. This nasty integral here just turns into negative of the volumetric flow rate. And so now we can piece together the surface integral over the entirety of the surface. And this just winds up with minus, this winds up being minus v dot 1 plus v dot 2. And this gives us that v dot 1 is equal to v dot 2, and that's equal to the volumetric flow rate. Okay? And so now we know that v dot 2 is equal to v2a2, and we know v dot, and so we can just really use this expression here to now solve for v2. Okay, so now we can find the we can now use this result from conservation of mass to find the velocities v1 and v2. Okay, so we know that v dot is equal to v dot 1. That's equal to v dot 1 a1, and that equals we know the diameter, so we know that a1 is pi over 4 cap d squared times v1, and we can solve for v1, and that implies that v1 is equal to 4 times the volumetric flow rate over pi d squared. Okay, and we do the same thing for v2, and here we basically wind up with the exact same thing, and we just note that it is small d rather than cap d because that's the diameter of the smaller portion. Okay, and so that's how we do that. And then now we take these two expressions here for v, for the velocity at station 1 and station 2, and we sub it into our earlier result for h. And so then we had h was equal to this right here, and now I'm going to take these two results here for v1 and v2 and substitute it in, and then what we wind up with is for v dot, this should be squared, squared times this ratio over here divided by g over sg minus 1. Okay, and then you could simplify it further if you wanted to. Okay, and so yeah, I forgot the squared, and I know that my final reduced answer, which is underneath this white box here, is incorrect because I just noticed a note, or I just noticed an error. Okay, and so and so here, yeah, all I did was I just substituted in the results for v1 and v2 and substituted them into this expression here. Okay, and so this problem shows how you can string together multiple concepts to solve a problem. And so these make great problems for studying for this class because really in solving this one problem, we've used almost every single concept that we've learned in class up to this point. And so these types of problems, if you want extra practice, I'd recommend going into the book and looking for problems that involve reducers and manometers and things like that. They are really great for practicing all the principles that you've learned thus far in class.